So my hope in this conversation is to make this explainer together and to help people see what's happening right now in AI, really, and what is the future that you see coming. What are you hoping to do in this conversation?
A lot of the reasons that I got into AI 30 plus years ago now is to advance science and medicine. And I've always thought of AI as potentially the ultimate tool to do that. So I'm hoping we're going to talk about that today. And really, that's been my passion for what to apply AI to, although of course it can be applied to many things.
Oh, this is going to be a lot of fun.
Yeah.
So in this Jenga game that we have, a lot of these are blocks that people will have heard of, right? These are, this one is Gemini.
Right.
But I would argue that the ways in which AI is meaningfully shaping people's lives most are the things that are invisible to them most of the time. So I want to start by talking about the project that you won the Nobel Prize for.
AlphaFold. Right. Yeah. Good Jenga playing.
I want to tell the story of AlphaFold with all of its drama because some people might not have heard it. But then I want to get really quickly to the cutting edge of this sort of category of sorts. Why did you decide to tackle this problem out of all of the many?
Well, I came across it actually as an undergrad in Cambridge. So I had a lot of biologist friends, and one of them specifically was obsessed with what's called the protein folding problem. So proteins are what everything in your body relies on. They make biology possible and living possible. And what's important about them is their 3D structure. So in the body, they fold up into kind of 3D structures, and those structures determine what function they have, or partially determine what function they have. And so the protein folding problem is really about, can you predict this 3D structure just from the one-dimensional amino acid sequence? So that's the kind of 50-year grand challenge of protein folding. So I love challenges, I love puzzles. So I couldn't resist it from a scientific point of view as this probably, is described to me as the equivalent of Fermat's last theorem, but for biology. So who couldn't be interested in that? But also when I first heard it, I thought the kind of problem it would be suitable for AI one day, even though of course, this is in the late 90s, we didn't have any kind of AI that would be possible to work on this. But I thought one day that would be possible. And then the final thing was just the impact it would make if you cracked it, because it would open up all these downstream possibilities for research, and especially in things like drug discovery and understanding disease. So, which I think is, the most important thing to apply AI to is improving human health.
And the reason that this would be huge for human health is that up until now, in order to develop new medicines, we'd had to spend hundreds of thousands of dollars and years of human effort to find out the structure of a single protein by shooting X-rays at it. So we had figured out some protein structures, but it was slow and expensive. So I'm skipping over an enormous amount of hard work here by you and your team. But I think by the way that I'm asking the questions, it is very obvious to people that you solved it.
Yeah.
So there's this moment where you realize that it is genuinely useful and you have solved what had been called one of the most important unsolved problems in modern medicine. And it's 2021. You're in a meeting. I am so glad that there was a camera in this meeting.
Yes,
because
randomly.
It is one of the most incredible moments I have ever seen.
Can we use AlphaFold to solve it?
I think you're talking with your team about setting up a system where scientists could send in a request for a specific protein, like a website, and then get the protein folder.
Yes.
And then someone else has a very different idea.
Yes.
Can you walk me through what happens in that meeting? And then your reaction is incredible. And I really want to know what you were thinking.
Yeah, sure. Well, look, it was funny that the cameras were there, happened to be in that particular meeting. It's crazy that it was that day. They very rarely followed us, but it was for that meeting. And normally what happens for these sorts of prediction models is the traditional thing is you kind of set up a server and then other scientists send you their protein sequences. And they say, I'm interested in this protein. Can you send me back the predictor structure? So, and that's how it's been done in the whole field for the last 40 plus years. And the reason is because most of the prediction algorithms are quite slow. So maybe it would take a few days and then you'd get back you'd email back the structure and then you'd ask for the next one. But once I realized sort of in that meeting actually that how quickly, not only how accurately we could fold the proteins, but how quickly, in a matter of seconds. And then I was just sort of doing the back of envelope calculation, like how many proteins are there known to science, known in nature, 200 million, and then how many computers do we have, and how many would we need, and then and then if we folded one every 10 seconds, and I sort of realized, sort of in the middle of that meeting, I was fiddling on my phone that it would be possible in a year. And so why go to all the effort of building the servers and the databases and the emails client and all of that when we could just actually fold everything ourselves, everything anyone could ever request and ever want, and then put it on a database somewhere for free for all the scientists in the world to use. So it just suddenly hit me, we should just do all that.
Now
That's way
you can
better.
really.
Why don't we just do that?
Well, so that's one of the options. Like
Right.
There's this.
We should just run. That's a great idea. We should just run every protein in existence, and then release that. Suddenly, all these things must have been going on in the back of my mind, and I suddenly realized that would be the obvious thing to do, and it would be actually probably less effort than standing up the server. So actually, it would save us time.
And you, in that meeting, your reaction is something like, why don't we just do that?
Yes.
That would be way better. We should clearly do that. And then you do.
All of a sudden, this crucial process that had been so hard is suddenly fast and easy. And it's being used by scientists all over the world. This huge unsolved problem, now solved.
Is it correct to say that we have now predicted the structure of almost all proteins known to science?
Yes. And we keep updating it. So every time, somebody scoops a pail out of the ocean somewhere, and then, there's loads of different types of organisms in that bucket of seawater, and then they sequence them all. And so the sequencing technology has obviously improved many orders of magnitude since the human genome was sequenced. So now the problem was the structural biology, the finding these 3D structures was lagging far behind the genetic sequencing. So now with these computational resources like AlphaFold 2, we can actually keep up with, here's a new million genetic sequences from some new strange organisms we found. Here are the structures. And so we have a small team at the European Bioinformatics Institute that keeps updating every year, all the new sequences that have been found that year. So we're now, always at the cutting edge. Like we know what all of these different protein structures mostly look like.
That's so awesome.
It is pretty amazing. It's especially amazing actually for the people, researchers that work on slightly more obscure, organisms or animals and things like, for example, wheat. I found out a lot of plants have way more genomic data than mammals and humans, which is very strange. They seem to have multiple copies of their genome and things, and it's a kind of strange and bizarre world, I think, the plant world. But my plant scientist friends of mine is like, they don't have the resources. Like with, the human genome, there's a lot of work's been done on that. But some of these more obscure organisms that's still really important for humanity, like crops and things like that. Now we're able to immediately jump to the science around what they want to do with the proteins, maybe help them be more resilient to climate change, things like that, and they can jump straight to the problem they're actually interested in, rather than getting bogged down with trying to crystallize the proteins that they're interested in. Another boon is for researchers who work on neglected diseases that affect primarily the more developing parts of the world, things like malaria or Chagas disease or leishmaniasis. They affect hundreds of millions of people around the world, and but there's not a lot of money in that if big pharma try to research that and find cures, because they're in the more poorer parts of the world. So they tend to be neglected, the research that goes into that. So there's these amazing non-profit organizations that do the research on that, but they don't have a lot of money or resources. So giving them the structures of the proteins that are involved in, say, malaria virus is a huge boon for them too, because they can go straight to the drug discovery phase.